Hello, Pradeep. I'm audible.
Yeah, yes, sir, you're audible.
Okay. Hello, I am audible.
Yes, sir.
Okay. Okay, we will start today with some previous concepts like flow, stream flow, curved stream flow, and we'll also today discuss about the Francis uh, queries regarding the momentum transfer, Moody's Moody's chart, and the capillary wave, buoyant force, and one more. I think I have noted down. No problem. Pitot tube concept. I think Francis, you're clear in the previous classes. So, this
Yes,
class,
sir.
yeah, this class will discuss more about your all queries, and I hope today all we your doubt will clear. So let us start. Don't wait much. Okay, now welcome in week 10 fluid mechanics live TS session. So basically, week 10 was about the differential analysis of fluid flow. This was the second lecture, second week on that differential analysis of fluid flow. First, and the first differential analysis of fluid flow, first was the week 9. In week 10, the lecture 1 is about the Navier-Stokes equation, and it's all about the Navier-Stokes equation, lecture 1, 2, 3, all. So basically, I have taken some question from the uh, previous assignment like NPTEL Fluid Mechanics 2021. So, but that year in 2021 or maybe the previous year, the question related this topic was not there in the assignment. That question was related to the boundaries value. Let's I want to show you. This is the boundary layer. The all question was about based on the boundary layer concept. So we will solve these are the question on the boundary layer concept was covered in the your week 11. So we will solve these all the question in the week 11, that is in the next live session. Today what we will discuss? Today we will discuss about the concepts about the Navier-Stokes equation and the Francis doubts we will clear. There's a very important doubts, a genuine doubt. So and one very important concept of the stream flow on the curved streamline. So what will happen? Let us focus on that. I think slide is visible.
Yes,
Yeah,
sir.
a bit but
Okay.
faint, but it's visible. Yeah.
Okay, slide is visible, no?
Yeah.
Okay, so here what today we are going to discuss the concept of streamline. When the fluid particle is moving on a curved surface, curved streamline, what will happen? So we'll start from the very basics, and it is very important. So might be this figure. Let me take the pen. So I think this figure is visible to all of you. This one. When the particle is moving, let's say this particle is moving on a circular path. Let's say uh, the stone is coupled with one wire, or you say the string, and some rotational motion is uh, in the stone. And what is happening once the rotation is start? like your particle is moving in the curved path, what will happen? One force is acting, actually one acceleration is acting towards the center, and you say the force, and this is known as the centripetal force. This is happen only when your particle is moving on a curved path, not on a straight. When the particle is moving a straight path, there is no concept of the centripetal and centrifugal force, whatever. But once the and force, you know already, the force is equal to mass into acceleration. So whatever the acceleration is there is the normal acceleration. So when the fluid particle is moving in the streamline, what will happen? Let's say we are going to focus on this streamline. It is visible. Hello.
Yes, yes,
What
visible, sir.
whatever I am writing, it is visible.
Yeah.
Yes, sir.
Okay, Mohan, it is visible. Please, Mohan. Okay, no problem. So we are going to focus on this streamline. The previous day, like week, the first question was about in the week 9 was about the when fluid particle is moving in the curved surface, what will happen with the acceleration thing. So, but in the question was given the streamline is parallel and equidistance things. So equidistance means what? The all well, let's say the fluid particle is moving in a pipe, in the bent pipe, or this is not like that. Many streamlines is there. So I have drawn here the distance between the streamline is same. Just for your visualization, I have made some bigger thing in the zoom view. But we are going to focus on this streamline. What will happen if the fluid particle is moving in the curve? The normal acceleration is developed by the concept of this, whatever I have telling. This is the basic physical concepts. So and what will happen? So that is the normal acceleration will exist. There is no issue. Why? Because of the normal acceleration. When fluid particle is moving on curve, the normal acceleration exists. Here I have written why exists, because of the curve flow, that is the centripetal acceleration. Now coming on the your tangential acceleration, what will happen in the tangential acceleration? uh, the distance between the streamline is same, and you know the concept of mass flow rate. Here I have written y tangential acceleration is 0, and y I have written y tangential velocity along the streamline is constant. If the velocity is constant, it means the your acceleration will be 0. uh, you know the mass flow rate. Mass flow rate means how much mass is entering at that point and how much mass is outflowing from that. So here what is your flow was steady in that question. First question was the steady and and parallel, that is the equidistant things. So what is constant? Rho is constant because of the water is flowing, or maybe there's another liquid is flowing. A is constant. Why A is constant? Because of the equidistance things. There is no change in the A. Only what is remaining, only velocity is a variable, which is also be same along with the streamline. Why? Because of the conservation of mass. That is the how much mass flow from here and how much leaving from here. So your rho is constant, A is constant, only V is variable. So if the if the area is constant and rho is constant, for the constant m, V should be constant. So that is why from here to here, your velocity will be the constant. That is the tangential acceleration will be the 0. Now coming on the next thing, this this is also very important. Here what is happening? Your streamline is moving like that, not not equidistance. What is happening? This side, the let's say the this length is L, and this length is how much? Let's say the L minus something minus, but L is, that is the, this is L1, let's say. So L is greater than L1. So what is happening here? Your streamline is coming, and here what is converging at that point? Converging means the space between two streamline is very less as compared to this point. So what will happen? From this point, mass flow rate is this much, and mass flow rate, that is the mass conservation of mass, should be valid along the streamline. So what will happen? A, your velocity, if the area is changed, density is, in this case density is constant, there is no issue, but area is changing because of the, here more space for entering, but for leaving the space is less, so area is changing. That is why the velocity also be changes along the streamline. So in this type of streamline flow, the tangential acceleration and the normal acceleration is always there. So in the equidistance things, there is no tangential acceleration, but if the streamline is converging or diverging, let's converging means this, your streamline meeting at a point, meeting not meeting, that is the area of flow is less, and diverging means this, from the, that is the diverging means this is less as compared to this. So in this case, your tangential as well as normal acceleration will be exist. If the streamline is a straight, then if the velocity is changing, then it will be the only tangential acceleration. There is normal acceleration, there is no concept in case of the straight streamline. Only curved streamline, the concept of normal acceleration will be, because of the, I have explained, because of why, because of the, when the particle is moving in the curved path, normal acceleration is exerted towards the uh, center. So this is the whole idea about the water flowing along the curved path, or you can say the curved streamline. So hope, I think you all people got what I am telling. Yes, Pradeep and Francis and
Yes, sir.
yes, Sarif, what about if you have anything you can ask?
So actually, for a streamline, the velocity at a point will be the tangent to that point. So we are resolving the tangential component along the streamline. See, in order to get that the velocity component perpendicular to that curve.
No, actually I'm not getting what is your question. Your
Uh,
question is about the normal acceleration, you are
uh,
telling?
so actually, I think in the last lecture, I just want to confirm that we are actually resolving the tangential component along the streamline in order to make the velocity component at that point perpendicular to that. Perpendicular means the tangential to that curve.
Yes, definitely. Here, if you will
Okay.
see in this question, what is the, whatever I have drawn here circle. In this circle, if you will see, visualize clearly. The drawing is not clear, but this is the tangential velocity, and just this is the perpendicular. That is a 90-degree. I would do this. The perpendicular thing, and this is a very basic concept. How the centripetal acceleration is coming, come in the picture in when the particle is moving around a circle, from the very basics. I think from 10, 12, you know this concept. And now we move on the next concept. What about your,
So, uh,
yes?
actually, is there a reason that we call that velocity along the streamline tangential? I mean, actually, the tangential means it will be perpendicular to that radial line, isn't it? And the actually the flow across that streamline will be constant when we resolve in order to get, but we are resolving it to the streamline, isn't it?
No, no. Tangential means here, Francis. What is the meaning of tangential? What is the here curve is given the along the curve. Here the tangential means meaning the along the curve the velocity component we are going to see how much the velocity is varying with this curve, right? And normal means just if you draw here the tangent and this is the normal thing, that is the 90-degree between this. Okay, tangential means this. This is the tangential velocity and this one is the normal. Okay,
Okay, sir.
now we'll moving on the your next question. Your next question was about the elasticity of the fluid. So here elasticity meaning in case of fluid you don't think confused about the solid mechanics. In case of solid mechanics, when you apply the force on a steel, let's say the steel is the best example, some amount of force after releasing the, not much force, some amount of force after releasing the force, uh, your particle is moving at the same place. So that is the elasticity in case of solid, but in case of fluid this is not going to happen. But in case of solid, in case of context of fluid, typically the elasticity means the bulk modulus. You know, the bulk modulus of elasticity is represented by this expression. The mathematically we can, and quantitatively you can say, we represent these things. So what is bulk modulus? This is a measure of how a fluid responds to change in pressure. It means what? For unit change in the volume, how much force is required, how much pressure is actually, how much pressure is required for changing the unit, your unit volume. So this is the meaning here, not the as you don't think, don't correlate with the elasticity kind of thing with the solids. In case of fluid, we talk about the bulk modulus of elasticity. So you can take the screenshot of this, and lots of point I have written here. You can read also. It will be
Okay, sir.
okay. And everyone can take the screenshot of the previous slide also. It will be help for you. This thing also, and this one also you can take. So basically the if the bulk modulus of any fluid is very less, let's say that you compare the bulk modulus of fluid A and the bulk modulus of fluid B. If the bulk modulus of fluid A is greater than as compared to the bulk modulus of elasticity of B, what will happen? In case of fluid A, your pressure is and we need to change the volume in volume, unit volume in all both fluid. If you want to change the unit volume in both fluid, what will happen here? The pressure will more required as compared to this, because what, the k is your directly proportional to, and it is practically we have this expression, whatever the mathematical expression and what is, you have seen the empirical equation, all these equation and these are the based on the concepts, that is the which follow the natural. uh, we are when we write some formula, and when we describe, when we discover some formula, when someone discover a formula, he correlate with the nature. If nature is follow this thing, then some you have seen the very good concepts and formulas. So this is already proven. If the pressure is, if someone if some fluid is need the more pressure for unit change, then bulk modulus of elasticity will be there. That's why that it is correlate directly proportional to this. So now your question was about the capillary wave. So capillary wave, it's a very good thing. I have also learned something new. So this is the capillary wave is nothing but you have seen some, let's say the here is a open channel flow, and water is still. This is the water, and water is flowing like that, not moving. Water is stop, not moving. So you know all the liquid having some surface tension. Surface tension is what try to reduce the surface area of the fluid. And when here if you read the what is the reason behind it, the capillary wave is nothing but is a small scale water surface wave. If you see, just you google what is capillary wave, you can see what type of capillary wave, but what is the cause behind it, the capillary wave in the fluid, in the liquid. So the restoring of the surface tension, basically fluid particle, the surface tension of the fluid particle is loses and then restore, loses, then restore, loses, then restore. This phenomena is happening, and due to this your surface of the fluid, surface of your liquid is like the wave kind of thing, very small scale wave. So this is the known as the capillary wave. And what is the utilization of the capillary wave? Lots of research is going on this. In the oceanography, the capillary wave are important because they affect the exchange of heat and gases between the ocean and the atmosphere. So lots of applications is there, lots of research is going on. So this is the capillary wave. Conclusion is that if you, someone asks you and some in exam if come the capillary wave, you just simply write the capillary wave is a small scale wave, and the it is due to the surface tension force restoration. This is the whole concept, and you just take the screenshot. Lots of example is there. I have taken some example also. So this is this. So you have take Francis. If you want to ask something, you can ask about the capillary web.
Yes, sir. Understood, sir.
Okay, okay. Now moving on your next doubt. Actually, if how many students today are joined? Okay, if any student want to ask some questions, just I have today I want to also write my mail on the chat box. Francis send me the I think in around 10 questions. Francis, how many questions you have sent me? 10 questions, right? Around 10, not exactly. I didn't see. But if someone having some problem, you can send me the screenshot of your question, or maybe if you want to write question on, you can write question in the mail also. So it will be I will be very happy if you have any doubt, because of by your doubt my concept also clear. So I have written here my uh, mail id in the chat box. So if some student, I think, sorry, if you have any questions, you just write me on the my mail id. And Palak, if you have any questions, you can also write, no problem. So now moving on the next your doubt. Or your next
So,
doubt was yes.
so one more thing about that streamline is actually is the streamline only considered in the 2D form, or do we consider that streamlines in the 3D form also? Why I ask is that if we are only concerned about that 2D form, there should be a component in the other dimensions also,
No, no,
isn't it?
no. Streamline maybe streamline is okay. Streamline is 3D. No, no, no. This is not the case. This is not like that.
So, do we call it, those components normal to that planar component, or we just consider it as the other convective components only? And those directions they will have normal and tangential component also in the z and y direction.
No, actually, Francis, your question I'm not getting what you asking, but what I am feeling, what you are asking, the streamline should be the 3D. Yes, 3D streamline is possible. Not this is case, because the x direction flow and y direction and z direction, the flow
Excuse me,
is
sir.
all three direction, so it is possible.
Excuse me, sir.
Yes, yes.
A stream function is function of only x and y, not z.
Yes, yes. Okay, okay. I will explain. No problem. Today, let me take the stream function. Then I
It is
will.
one. It is only with respect to field, not volume.
Yes, yes, yes. Just I am telling the concept about the stream function.
Where
Just
potential lines are functions of x, y, and z also.
yes,
And
yes. Why we are constant on the 2D in case of the stream function? Let me explain. Let me explain some mathematically concept. I think what here I am writing, it is visible. It is visible.
Yes, sir. Yes, sir.
Okay. This is the continuity equation, you know, all the incompressible fluid. Uh, this is the W component. It is equal to 0, right? For stream function, why we are using, it is a mathematical concept. Just we are try to reduce these things. Just we are try to write the equation, this equation in the function of stream function is a why we are constant on the 2D, not 3D. The reason is the stream function should follow the your continuity equation is, so this is the concept. If we going to write the equation for W stream, in case of the stream function, you know, u is equal to what, uh, del psi by del x, I think del y, and v is equal to minus del psi by del x. So we have defined these things. That is the your stream u in case of the in terms of the stream function, and v in terms of the stream function. If we are going to define the w, it is a mathematically mathematically it is very very complicated. So mathematically we cannot define these things, that is the w component of the in terms of the psi, because defined is the good thing, but whatever you are going to define, it should follow the continuity equation. If it is not follow the continuity equation, there is the no meaning of the your define. Let's say if you are if you will write the w is equal to, let's say, whatever, if you writing here, there is no meaning, because of that it's not satisfy the continuity equation. If this value is, if you put in this, what is happening, del u by, that is the del y del x, and del psi by del y. Now del by del y and minus del psi by del x, and the w in case of 2D, I am going to write 2D is equal to 0. So what is happening here, del psi by del x and del y minus del psi by del x del y, it is 0, it is equal to 0. But when we going to write in the w with respect to something, it is not equal to 0, that is the mathematically it is not possible. So why we just for it is a mathematical concept in the psi, whatever you are telling the stream function. So this is the nothing, just we are just we constant y2d because of the mathematically follow the continuity equation, that is the del u by del x, del u by del y, and del w by del z is equal to 0. not possible using the 3D, that is your psi is a function of x y z. So the main conclusion is that why we are constant, because of the mathematically not possible to follow the continuity equation uh, in case of the when we talk about the 3D thing. So hope, I think some might be I am able to explain you.
Yes, sir. So, can we say that the streamline flow will be mainly considered for 2D
No, no,
flow?
no, no. You cannot say
Okay.
streamline. Yeah, streamline is not considered 2D. The stream function you can define for 2D only. It is not like that. If the stream function may be 3D, but stream function, this concept is only about the stream function. Why we are concentrating on the 2D only in case of the stream function. So
So,
yes.
in the previous case, why we didn't consider that Z component? Actually, there is an X and Y component. Is it? We are considering, but why we are not considering that Z component in that streamline?
No, no, no. That question was okay, okay. You don't confuse with the normal thing and the tangential thing. So basically, what
Yes, sir.
here? Let me explain again. Your tangential means what? Let me take the new. Your tangential acceleration. If the I draw that this thing, your tangential acceleration is what? The velocity along the streamline, right? If the velocity is varying along the streamline, let's say here v1, here v2, here v3, then tangential acceleration. Normal means what? If the streamline is curved, then normal acceleration is acting on that. So this is the normal. You don't think this thing. If the vector is there, then this is the your u, this is the your v, and let's say the this is your w. You don't confuse with this and this is the velocity vector along the streamline, and the normal thing is that if the curve is the additional acceleration is coming. So this is the meaning. uh, I hope, I think Francis,
Okay, sir.
your doubt is
Yes, sir.
okay.
Yes, sir.
Now we moving on your next doubt was I think some who was asking about that. Let me Palak, I think your doubt is clear. Why we constant on this 2D thing in case of the stream function?
Yes, sir. Yes, sir.
Yes, okay, okay, thank you.
Because this is tangential always along the surface only.
Yes,
If it
please,
is
please
not,
again.
yes, that will act in the volume, but tangential means along the surface.
Yes, 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 along the surface. So I think if you, Palak, if you have any doubt, you can also mail me. Uh, no doubt. If you have any doubt from, I think you today was your first day or some day you have attained some previous day.
I think 3, 4 days I was attended.
Okay, okay, it's good. Okay, okay. So if you have doubt, you can ask, because by your question, my doubt is also clear. So I am very, very happy with your
Okay,
doubts.
sir.
There is no
Thank
issue.
you.
Okay, now we'll moving on the distorted model and the undistorted model. It is very, very. I think I want to give example on that. So I think Francis, your doubt will be definitely clear. So undistorted model means what? If you are going to, let's say, your car is there, this is the actual car, and your this is the model car, and one model is also there. They are similar. These two thing is similar in the length, width, everything. If you are going to you're going to experiment on the similar thing. Whatever is car is there, the dimension, let's say the x y z. So here also the dimension is x y z. There is no change in that dimension. But in case of the distorted model, this is the undistorted case. In undistorted case, same replica should be there for your whatever you are going to make the product. But if you are going to the distorted model, your dimension should be less. So this is the meaning of the distorted and the undistorted model. For example, in the aerodynamic case, what I think your mechanical background is there, so you can easily correlate. In the car manufacturers often use the undistorted scale model. In case of the when we going to the wind tunnel test, how the streamline is happening on the surface of the car. So what the car manufacturer, what they are doing, they make the car, and some video I think you have also seen from the Tesla. I think he was testing the car. I think in the, I think bulletproof kind of thing. Some video was viral during that. So on that type of experiment known as the undistorted, because of the same replica was there, and you can say the actual car was there. But in case of the distorted model, you make the small things as compared to your uh, and I think you technical term all you know the whatever we are going to geometrical similarity and the kinematic similarity, dynamic similarity. Sir was covered very well, and I have, I think, also covered some concept about it. Francis, I think your doubt is clear about it. This is not a big concept, but it
Yes,
is a
sir.
very very important. So now we moving on your next doubt.
So actually, for the is there any cases in which we will be learning about that the undistorted the prototype model? I mean, there was a
You are asking the example of undistorted, Francis?
so what one minute.
Okay, just I think I was given the one example of the car experiment of the wind tunnel test. Francis, exactly what is your doubt? Please tell again.
So you can move on. I will ask in the end. I mean, I just want to read that again. Okay.
Okay, okay.
Okay, sir.
Now we'll moving on the your next doubt, the buoyant force. You know the Archimedes principle. The is one line I have written, very very simple thing. The buoyant force, also known as the buoyancy thing, is a fundamental concept of the fluid mechanics and physics. It refers the upward force. Okay, upward force exerted on the object submerged in the fluid. Let's say for the example, if let's say pond is there, and in the pond I have put one big log. That is the log is dry log. So whatever the force is acting on that in the upward direction by the liquid, so this is known as the buoyant force. If you, let's say the FB, and this is the FW, that is the weight force. If your weight force is greater than FB, what will happen? It will be the sink. If FB is greater than FW, floating case. So this is the concept, and you know the Archimedes principle. What is happening? What was telling the Archimedes? For that, you can take the screenshot. The force is how much actually will act. The Archimedes was telling if the volume, let's say that this much volume was sink in the water body, then your how much the weight of this actually, how much your this volume replace the water from that from this location, that volume will represent your actually the force, that is the buoyant force that is related to the buoyant force magnitude. So I think it is also clear, and it is useful for, I have given also the application thing where we use in ship, submarine design, hot air balloon and all.
Excuse me, sir.
Yes.
I want to know how to calculate the buoyancy force when the object is moving inside the fluid. Suppose if it
Okay,
is
in case of
floating,
moving, okay, okay. Or in case of moving, I think some another analysis is there, but we are what I think we have a study in the fluid mechanics in case of the static, but some force was also, let's say, let me the explain little bit, whatever based my own knowledge. So let me this is the, you can assume this is the ship. So if the ship is moving, that is a velocity v, and the weight is still on the downward direction, in the downward direction, and this is the buoyant force. So definitely in case of moving, maybe some another force should be included in the, I think as per my base knowledge, if the thing is moving, there's some another forces acting on that, so this will also be included, but the majorly your weight of fluid, and the concept is that the behind the buoyant force, the weight of your body, that is the your, let's say the ship, and how much force is acting exerted by on the floor of your ship uh, from the water side. So this is the whole concept, but definitely I will see this question, if the fluid is moving, then how we can calculate exactly, because I have never seen this concept. Okay, okay plug, we'll see this question.
force here, force is depends upon velocity
Yes.
and dynamic viscosity
Yes.
and also dimension, physical dimension of the object.
Yes, if you are talking about the shear force, definitely it will be depend on that.
Okay, sir. Thank you.
Okay. But Palak, I will definitely this way I will explain in the next class. If the object is moving, then how the buoyant force mechanism.
The object is moving in the vertical direction,
You
vertically
are,
downward direction, vertically downward direction.
oh, you are
Suppose if we draw
you,
sphere in the fluid, the
yes.
sphere will travel in inward direction. How the buoyancy force will act on the moving object?
No,
Sir, I think
moving
he's
in the
asking about the
moving in the
submarine.
downward direction you are talking about, or the lateral direction.
Downward diameter.
Okay, so you, I think you might be heard about the Stokes law when the particle. Your background is a civil background or what? Your
Mechanical.
mechanical. You also, I think you know the when water when something is sinking in the water, then let me explain. I think I know this concept. So let's say the one tank is there and filled with water, and some particle is sinking and travel like that. So buoyant force is also there acting on that, but buoyant force, whatever I was telling you, the buoyant force is not much enough which float the particle, whatever the particle, but it is acting on that along with drag force also acting on that, because it is the moving condition. Okay, so how it will be the balance, and here and the weight force is also there. So W plus W is equal to how much, for the, if we talk about the equilibrium condition, W is equal to this FB and this one also. Let's say this is the D, FD, FB and FD. So your weight of particle is equal to your buoyant force and your drag force. Whatever the drag was acting on that by the side of the fluid, that is the drag force if the particle is moving in the downward direction. So what we are actually considering when we calculate the weight, what we do, we just take the submerged weight WS, that is the your solid and the your water, let's say the water, and the G. So when we write these things, then this ws is equal to FD. This two thing is included in these things. So this is the whole concept. This type of force is working in case of when the body is sinking in the downward. I think hope some I am able to. So this type of force acting on the when the body is sinking in the water body. Okay, plug. I think you got the.
Okay, sir. Okay, sir.
Okay, and if you more know about it, you just Google it. Google the Stokes law. The Stokes law, when the particle is moving downward in the water flow, then you definitely got this. The concept is this, but if you want more thing, then you definitely go through the. But
So this going for okay, sir.
yes, yes, Francis, you can ask, no problem.
So is this going force a body force?
No, 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 no. Body force not. This is buoyant force is acted. Actually, it is caused by the fluid. Not actually the fluid is applying the force on the action reaction. You know, when some you apply the force on water, then water will also try to push upward direction. So this is the water force, not water force applied on the body, not body force. Body force is what? Mass of the body.
It will be acting on the center of mass of the body for the body force. Why I asked is that when a body is if for this case if there is a square block at the base of the container, then actually there is buoyant force acting on it. But if the buoyant force is acting on the surface, then how it can lift lift that body? I mean, the buoyant force is actually acting vertically, isn't it?
No, 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 no. You don't confuse. If let me explain. If your body is like that, let's say this is the surface area. Throughout your surface area, force is acting right, and also your weight is lots of. If you want to divide some little part of your, lots of weight is acting on that. Lots of weight is acting on that. Lots of weight is acting, but the whole weight is on the mass. Here, similarly, actually, why we are considering the for the mathematical, the mathematical expression, but this part is acting like that. This part of the body is applying the force downward. This part of the body, similarly, water also this column of the water applying the force. This column of the water apply the force. This, but for representation of the mathematical, what we say, the whole force acting on the mass center of the body, and when and your buoyant force is acting on the center of your surface, whatever is the surface area is there, this is on the center of, it is concentrated on the center of. Why? Because the each and every column applying the force and the balances by the this mass of. So I think hope Francis, your doubt is clear on that.
Yes, sir. So
Okay.
Excuse me,
if
sir.
the
Excuse me, sir.
block is at the basement, then I think the fluid won't be able to apply on that bottom surface, isn't it?
Yes, you just think in the different way how you just generalize thing. Your let's say that your box, rectangular box, is divided in the number of pieces. and joint it and make the big pieces. So small pieces of your box applying the vertical force, and similarly the water column below the your surface, below the your vertical column of your body. So similarly that much column is applying on the, if you just think the lots of slices of the your body and the lots of forces applied by the fluid on the body. So just for the mathematical expression we have.
Excuse me, sir.
Yes, yes,
Actually, as per my experience,
yes, yes,
this buoyancy force always acts through a center of buoyancy in case of submerged body.
yes, yes,
Floating body, the buoyancy force always acts along the metacenter, through the metacenter.
yes. If
In,
the floating body case is there,
in the submerged body, this buoyancy force always acts through the center of buoyancy.
yes, center of base is nothing but whatever the volume is volume space was
Yeah,
from the diverted from one place to another place by the when the body is sinking, little bit sinking. So
yeah.
the volume of center, that is the whatever the mass was expelled from one place to another, that center was buoyant force is acting on that center.
Weight of the body is acting through center of gravity of the solid.
Yes, yes. And the center of buoyancy. Actually, if you see in the generalized way, generalized view, not in the mathematical, at the general layman point of view, just for what we just, if you see this thing, let me discuss more. Yes, if you see the generalized view, not very the technically and kind of thing, just for, if your body is there, let's say some body is, I want to draw in the 3D view. Let us this is your body in the inside the water. Your center of mass, let's say the water is this much. So this is not the line, just I have. So this much volume is inside your water. So whatever is volume is there. So let's say the center of point is here. Your buoyant force act on that. Whatever mass is there, your force is act on that in the center of your body. But if you see as a layman point of view, there is, if you see the your box is divided, if you see it divided in the number of slices, and each slices acting, let's say the here number of slices is 1 2 3 4 5 6, let's say. So this much, if you going to consider weight this much weight is applying on that, that is the weight force, and this much water column going to apply the force on that. So each, let's say the slice, lots of slices of your body, and the lots of water column of uh, from the downward direction is acting on that. So but generalized point of view, if we want to tell whatever the volume was removed from the by the body, so on that, whatever, let's say the volume is this much is removed from, so at the center of your volume your buoyant force will be acted, and at the center of your uh, body your weight force will be acted. So this is the concept, not I think that much complicated thing. So it is, oh, I think if we think as a normal, that is not very technically, then we can definitely understand very easy way. So shall I move on the next?
Sir, I have one more question, doubt.
Yes, yes.
Suppose the body is oscillates.
Yes, body oscillate.
Does the buoyancy force and weight of the body in line with each other?
Please, again, you repeat your question. If
When
the
the body
body is oscillating, yes,
oscillates, does the buoyancy force and mass of the body force, that is
yeah,
the body force,
yes.
in line with both are in the same line?
Oh, no, 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 you just, okay, okay. Let me, if the body is oscillating, let's say your, like that, some, now I want to make the sheep like that, and your sheep is oscillating, sometimes upper, this region reach up to that, and this region reach up to that. So this is the case, I think you are talking, right?
Pitching condition.
Yes. So I think this is reach on that and this is reach on that. When the upward direction, this is will come on that place. When this is come and it come on that place. You are talking like that, right?
In case of pitching and rolling.
Okay. Yes. I got your doubt from that. But you are talking about the, let's say this is the buoyant force is the equilibrium condition, that is the your buoyant force is acting at the center of whatever the volume was removed, and your body force will act on that, right? Body force on the center of your mass. So you are telling the buoyant force, that is the line of buoyant force and the line of your body force does will be the same when the your body is oscillating something. Your question is
Yes,
like that?
yes, sir. Yes, sir. Yes, sir.
Okay. Oh, I think, but I don't exactly, but I don't exactly remember the concept behind it. But I think it should be not exactly on the same line. Let me, I will check these things. But I think, if you remember, if they exactly on the same line, just for as a generalized point of view, if we think, if the body is acting the downward direction and this is also acting on the downward, in case of actually the oscillating thing, one meta center, I think you know the meta center, I forgot about the concept. On the meta center point is there out.
Meta center point is a point through which
Yes.
the body oscillates.
Yes. So I think it is not on the same line. Your whatever your doubt is there. So based on the just you think on the generalized view, I think your buoyant force in case of the oscillating should not be the same same action of the line. But if you want, we'll discuss more about in the next class.
Yes, sir. You are right. You are right, sir.
Yes, just as a layman point of view, if let's say I forgot about the concept, but as if we as per our the just as a generalized view, if you think, if you know the terminology what is buoyant force and the body force, then just you think when the body is oscillating, what will happen? It will be that your force is acting on the similar. I think it should not be the on the same line of action, but we'll see the more about it. Maybe I am wrong, but it will. I will see. I will discuss more about it. It is a very very good concept. Okay, I think one more question of the Francis. Not more. I think three questions. The transfer of momentum. This is the very very important concept. Transfer of momentum is nothing but, you know, the momentum, if you go through the very basic things, momentum is nothing but what is mass into accelerate, mass into velocity. In case of the fluid flow, you know, uh, let's say the pipe flow is there, your velocity here, I think here velocity is 0, and at that point velocity is something. Here is the, I'm going to represent the uh, your magnitude in term, the maximum magnitude, the maximum length of the arrow. So this is like that, and here also 0, you know, the and that here also 0. So here I want to draw the one just half part. Here just half part I want to draw. So this is look like that. Your velocity is increasing from bottom to, if you say the bottom, these things, this is the u and this is the your depth wise, let's say the y, your velocity increasing towards the upper side. So what will actually the concept of the momentum transfer, you this lower velocity is try to, and why this happening, this magnitude is less here and here is the magnitude is more, here the magnitude is more, because of your wall effect, that is the no slip condition. Wall effect is propagated towards the upward direction. If if the magnitude is less, then what will happen, your density is, that not your velocity is more or less similar as compared to the uh, more or less similar from one layer to another layer. But as the wall effect is dominated at some depth, your velocity gradient is much. So here is the meaning of the momentum transfer is that your lower layer what try to reduce the upper layer, means reduce upper layer means velocity try to reduce. So momentum transfer is that your lower layer is try to reduce the upper layer, means what, means what, the momentum transfer means try to reduce your velocity, try to reduce the velocity of the upper layer, means the momentum transfer. So here the simple that is written in the different way. The transfer of momentum occur between the layer of the moving at a different speed because of the viscous stress. Viscous stress, you know, the viscosity concept and the no slip concept also. Viscous stress is what, I think, as per, if you see the Newton's law of viscosity, in case of the laminar we write these things. So your stress is depend on these things, viscosity and your gradient. Here the gradient is very very sharp, very much near the where up to much depth your wall effect is dominated. So momentum transfer is this concept, very basic concept is this. Your lower layer is try to reduce, means the momentum reduce. Momentum is what, something is moving with some mass, but someone try to reduce you. Let's say you generalize people what telling the someone influence the momentum of that guy, means what, they try to reduce the influence of that guy. So this is the, if you think in the generalized view, so this is the meaning is that every concept is come from the very basics and the physical and very nature, from the nature. So if you think like that, definitely your, Francis, I think your doubt is clear about the momentum transfer how happen
Yes, sir.
between the
Yes, sir.
layer.
Understood. So,
Okay.
one more thing. So we are drawing this parabolic form as zero at the wall condition, and it will be increasing upper layer since the fluid is flowing over the stationary plate. If the plate is moving and fluid is stationary, then the maximum velocity will be at the bottom.
No, no, actually, you are talking about this. Let me draw. If the you are talking the fluid is that is a plate, and fluid is there and one plate in the upper, and it is moving in velocity v, and your this is the stationary condition. Let's say the fluid is in the rest condition. You are talking like that, Francis?
Yes, sir.
No, no. You know, here the velocity is zero because of the no slip condition. Your velocity is zero, but here is what, your velocity is maximum. Here also the no slip condition is no slip condition is not means the zero. because of here your velocity of the plate is zero, that's why velocity zero. Here no slip condition means whatever is upper condition, that is our slip condition, the same follow the layer of the fluid. Here the velocity v, the same layer of the fluid also the velocity is v. So here is the velocity is maximum as compared to, if you see here the velocity is very very less, and here is the velocity is very very high. So
So
Francis, you,
if both the plates are moving, then we will be having non-zero velocity at the top and bottom.
yes, what you are telling?
I mean, if the plate on top and bottom is moving, then that means the fluid at the top and bottom will be having a non-zero velocity. I mean, the velocity of that moving plate.
Yes, definitely. The no
Okay.
slip condition is means that only. No slip condition is not like that. It is the velocity always zero. But no slip condition means if the plate having the velocity v, your fluid also having the velocity v.
So sometime we are drawing that parabolic, instead of parabolic profile we will be drawing some triangle like form. In which condition we will be getting that triangle like form?
Okay, okay, okay. Very good question. So let me explain the different way. I think in case of when I talking about the laminar and turbulent, I think that time I was explaining, but no, no problem. I will also explain here. In case of laminar, what is happening actually? In case of laminar flow, I will give the little bit just. In case of laminar, this is a pipe flow. Let's say the uniform flow is coming. And whatever I am going to draw here after the development length. I think you know the concept of the development length. Francis and other students, everyone
Yes,
know
sir.
the concept of the development length. So after development length, I am going to draw the all profile here, whatever I will draw. So in case of laminar, your velocity is follow the parabolic, right? But in case of laminar, but when the flow is turbulent, what is happening? In case of turbulent, the thing is very very difficult. But let me explain again. In case of the boundary layer formation, I think you know very well. One Prandtl concept. Prandtl concept was there when the turbulent flow was there. The fluid particle from one layer to another layer is moving. That is the length L. So is moving length L. So this is the mixing concept. The Prandtl give the mixing concept of the one layer to another layer. So this is the whole concept. As per this concept, Prandtl what telling, I think he was telling your the actually the turbulent flow. Let's say that this is the magnitude of the turbulent flow. It having two things. If we try to generalize, if we try to write the mathematical thing in the quantitative way, we can write these things, the average things and the fluctuation things. That is the fluctuation component. If we combine these things, it will give these things, the turbulent velocity. So Prandtl try to quantify these things using the this concept, mixing length concept. This is the hypothesis for given by the Prandtl. And he was telling your u dash is equal to del, I think I don't exactly remember, but he was given the u dash concept and the v dash. So from here one log law of, that is the your log law is coming in the picture. So in case of log law when the coming in the picture, and you know the concept of the boundary layer formation. In the boundary layer formation is something like that, and here the is very viscous sublayer. In viscous sublayer, fluid is follow the laminar, that is the linear thing. This is also having the derivation. If you want, I will explain in the next class, no issue. But in the viscous zone, the velocity follow the linear, and in the upper zone, velocity follow as a log law, not parabolic. So in case of the turbulent flow, your if you want to draw the your diagram, let me, this is the your straight thing from here, and this is the parabola thing, or not parabola, a log, and this is the straight. So this is the concept of the turbulent flow and the laminar flow. And if you want more discussion on that, frontal mixing length and all, will no problem, we'll discuss one day.
Okay, sir. Understood.
Okay, okay, I think now moving on your next doubt was about your, I think, okay, this thing I have discussed, your Moody chart, right? Moody chart is nothing but when flow is turbulent, you know this thing, HF, I think here written, head loss, major head loss due to the friction of pipe, FLV square by 2ZD, right? So in case of laminar, this is equal to what? Here if you concentrate on this thing, 64 by RE. But in case of turbulent, uh, the thing is very different, very difficult. So equation was given by the Colebrook. If you want to lots of experiment, after the lots of experiment, this equation was come. So the Colebrook is given these things. You can calculate the, in case of the turbulent flow, you calculate the F based on this equation. So Moody what does, he just draw the, actually this is nothing but this is the representation of this equation, with the different roughness of the pipe. Let's say the lots of pipe is there, steel pipe and the cast iron pipe, lots of pipe is there. So here the epsilon means roughness is there, like E1 and E2, and diameter is D and diameter is D. So here is written this thing, the relative roughness, and this thing is the your friction factor, dash is friction factor, and this is the Reynolds number. So combining these things, Moody's basically draw the uh, graph of this equation. Lots of experiment was there, lots of comfort was there. So itself it is having a on its history of the Moody's diagram. I will discuss some days, no problem. But the concept is here that after, if you look certain, this red dot line is what, after this red dot line, the graph is very straight. Means what, your, if this is, let's say for this, your friction factor is coming 0.4. If your Reynolds number, at that point your Reynolds number is 10 to the power 5. If you are coming at that point, Reynolds number is 10 to the power 6, but still is your friction factor is 0.04. It means what, after a certain time, that is your fully rough turbulent flow. In case of the fully rough turbulent flow, there is no dependency of Reynolds number on the friction factor. It is only depend on what, it is only depend on the relative roughness, which type of material you are going to use. If let's say your, for this, if we are going to use the material of relative roughness of this and this E by D. And if we having the Reynolds number is 10 to the power, let's say the 8, or 10 to the power, let's say the 6, no meaning of the Reynolds number when you are going to calculate these things, because you are in the straight region. So this is the some very important thing. In case of transient flow, you just here just see the three four thing is written here: laminar zone, and the transition flow, and the turbulent flow, and the fully rough turbulent flow. In case of the transition, both depend on both on the your relative roughness as well as Reynolds number. In case of laminar flow, only friction factor is depend on the Reynolds number. There is no meaning of the your uh, roughness of the pipe in case of the laminar flow. So this is the, but very important thing is that in the conclusion, in case of laminar flow, your friction factor depend on only Reynolds number. In case of the transient flow, transitional flow, depend on both relative roughness as well as Reynolds number. Your friction factor depend on both. Turbulent flow, still if you see the turbulent flow, it is depend on both. But in case of the fully rough turbulent flow, it is not depend on Reynolds number. So I think some very basic concept you got about the Moody's diagram. Francis.
Yes, sir.
Okay. Okay. I think we have we can take some break of the 5 minutes. Now we'll start the Navier-Stokes things.
Okay, sir.
So Francis, if you have any doubt, you mail me again. No problem. I will very happy if you will ask some such type of question. And every participants, if you have any question regarding any topic, whatever in the fluid mechanics basically, so you just mail me on my mail ID. I have written in the chat box. So we'll start within 5 minutes the Navier-Stokes equation. Hello, I'm audible.
Yes, sir.
Yes, sir.
Okay, okay, okay. So we'll start the Navier stroke. We have done the lots of discussion on the queries on the Francis and the another also students. Actually, in the previous classes we have covered the Cauchy's equations, but what the Navier-Stokes equation is going to deal in the Cauchy's equation, if you see the equation from 937, that is the in the previous classes I was covered, but just for your or this alternative form of the 948 equation, it is written here. It is not very useful to us because of the stress tensor. You know the stress tensor. This is the stress tensor is the representation is there. I think my pen is visible now. Now visible. What I am writing something. It is visible. The equation
Yes,
948.
sir.
Yeah, it is visible. Okay. So in the Cauchy's equation, it is not very useful. Why it is not useful? Here it is written something. We have the actually the unknown thing is very much as compared to the known equations. You know already the from the very basics, unknown and must be equal to the equation. Then we can get the answer. We can calculate the unknown thing if unknown and number of unknown is equal to the uh, number of equations. So here very important line is there. So in the Cauchy's equation is not very useful as because the stress tensor contain 9 component and 6 of which are independent because of the symmetry. So this is you I think you know very well. Thus in the addition to density and the 3 velocity component, there are 6 additional unknown for a total 10 unknowns. In the Cartesian coordinate, the unknowns are these things 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So all 10. Meanwhile, we have discussed only 4 equations so far, one continuity equations and the Cauchy's equation, that is the 3 equation Cauchy's. We have the 10 knowns and the only 4 equations. It is not possible to calculate the value of all unknowns. Of course, now what is written again in the further, of course, to be mathematically solved, the number of equation must be equal to the number of unknowns. Yes, definitely. And thus we need the 6 more equations because we have the 4 equations already, and these equations are known are called as the constitutive equations, and they enable us to write the component of a stress tensor in term of the velocity field and the pressure field. So this is the whole idea. What is written here, your the one extra thing, let's say this is the sigma x and the sigma xy. So these all term is the function of your known velocity or the pressure things, because it is written like that. The meaning is that we convert somehow these things in case of the your velocity component. So we know the velocity component, we can easily get the uh, uh, unknowns value. So the similar thing is written here, just I have uh, copy paste. The first thing we do is separate the pressure stress and the viscous stress. When a fluid is at rest, the only stress acting at any surface of any fluid element is local hydrostatic pressure. When the fluid is rest, then what is only the force is pressure is acting on the surface of the body, whatever body is there, which always acts inward and normal to the surface. Yes, thus regardless of the orientation of the coordinate axis. Yes, you know already. So the hydrostatic pressure, that is the pressure in the case of the static condition, is same the thermodynamic pressure, which is we are familiar to. Actually, it is written in the terms of the book language. So the concept is here that when the fluid is in the rest condition, your force, actually your pressure is acting normal to the surface. But when the fluid is moving, then what is changing? When the fluid is moving, the pressure is still act. Whatever was pressure was acting on the normal, the pressure is still act. But viscous stress also may come exist when the fluid is moving. The viscous stress is also come, you know, from if we talk about the shear stress in case of the laminar flow, that is the Newton's law of viscosity, you know. When fluid is moving condition, then this thing will be, that is the your velocity gradient will exist, then shear stress will exist. So this is coming from here if the fluid is moving. Now where we have introduced a new tensor, that is the tau is called the viscous stress tensor, and the also we sometimes we call the deviatoric stress tensor. So but still we have some, what is written, just see the mathematically we have not helped to the situation, because we have replaced the six unknown component of tau ij with six unknown component of the, that is the sigma ij, that is, and the six unknown component of, just we have replacing, not we have some. But the thing is and have add another unknown, the pressure p, and another unknown pressure p is there also. So fortunately, however, there are constitute uh, equations has the expression tau is a in terms of the velocity, because you know the all the tau is a, it is very, just we was talking about in the previous, we want to write this thing in terms of the velocity. So in case of the stress term, we have the velocity term, so that is here written, the your shear stress is related with the velocity. So and velocity of the field and measurable fluid properties such as viscosity. This is related with two things: measurable property, viscosity, and your these things velocity. So the actual form of the consecutive relation depend on the type of fluid, as the discussed shortly. I think everyone got the what causes, actually what was the causes limitations, and here we are just reduce the causes limitations and try to find out something in terms of the velocity, known velocity term. Let us move ahead, because we have not much time. So but this is the very very basic things, how the things is shifted from one to another. Just you when you read some, then you can definitely get some depth knowledge, otherwise the shortcut there is no solution. As as a side note, there are the some sub that is this is not very very important thing. Okay, so actually the in case of the derivation of the Navier-Stokes equation, how it and one thing is very very important also, the tau is a is related with this, and this relation is given by the lots of researcher, that is what is written here, that is the Kundu. uh, in 2011 he gives the viscous stress tensor for a incompressible non-Newtonian, that is a Newtonian fluid with a constant properties. This is related with this your viscous stress. This is talking about the viscous stress. When you write in terms of the whatever in the previous this matrix is given, if you write in terms of this will become like that. And tau ij, that epsilon ij, that is your stress, strain rate tensor. And strain rate tensor we have discussed in the previous classes. I think in case of the when we were studying about, I think, dynamic chapter, or I don't remember exactly, but it was discussed. But here is a only you concentrate these things. How the unknown term, this unknown term is shifted in case of the known, because velocity you know and the mu is known. So this is the just calculation things, and finally your Navier-Stokes equation look like that. We are not going to discuss much here the mathematical thing. If someone need the mathematical thing, you just mail me your specific question. I have written the my mail ID in the chat box, and then we can discuss more about on the next class. Oh, this is not actually the in the Cartesian coordinate. Your continuity equation is for incompressible continuity equation is this what we are discussed in the previous slides. And your the Navier-Stokes equation is having the three actually the three component. In the x direction velocity is like that, the equation is like that, and y is like that, and like that. If you see here in this, only here four variables are there in this equation. The three-dimensional incompressible fluid flow, four variable or unknowns. One is pressure, and the three is the velocity. Sometimes somewhere people asking about the if we have the Navier-Stokes equation 3, and why we need the additional, and we have the velocity 3 component and the 3 equations, why we need the continuity equation for solving the unknown. So one you always remember the pressure is also unknown is there, so that's why we need the 4 equations. That sometimes this question was asking. So differential analysis, you know, the what we do actually in the this differential analysis of the fluid flow problem. What we do, calculating the pressure field for known velocity field, because here what is velocity, and only the here thing is velocity and pressure. If you know that is the your velocity and pressure, if you know the velocity, then you calculate the pressure thing. And calculating both velocity and pressure field for flow known geometry and the boundary condition. And sometimes you need to calculate both things, velocity and pressure, on the basis of the geometry and the boundary flow condition. Boundary condition means what? I have some slides also about the boundary condition. I think some equation, some problem I have, but let me discuss about the boundary condition.
So
Yes,
there was one viscosity also, sir. Viscosity also, there was one viscosity also earlier, is it? So that got vanished.
yes, where is?
Like the previous slide you saw here, there is a previous slide. Uh, yes, there is a viscosity term here. Yeah, next, sir, next. No, no, no. Yes, yes, there is here. The viscosity term also is there, is it not?
This one, you last one you are talking. This
This
one.
one, the incompressible Navier-Stokes equation. We have
Yes,
viscosity.
if you see this thing is written in here, what is written? This is a viscosity term. The similar thing is written, but this is written in terms of the vector form. Your the divergence thing is there, and but if you see similar thing is written here only at the place of the divergence things. What is the divergence? Del by del x plus del by del z. I think you know these things. So only the things is written like that. If the square is, so square is there. So you are talking about the viscosity term neglected. No, no. Why it will be the neglect? No, viscosity term will not be neglected. Your viscosity is actually your shear stress is related with what? Mu and del u by del y. What was the matrix was there? In the Cauchy's equation, what was the problem? There was no relation such kind of. But Navier-Stokes equation, we have converted the sigma to in, that is your case of this in the shear stress, and shear stress you are related as per the Newton's law of viscosity, you know, velocity. So here is not neglected. This is written like that. So I think Pradeep, your doubt is clear.
No, sir, not clear because still the mu is still there in the equation, is it not? Uh, until 9.61 d also it is still there. It is not vanished. So somewhere probably we're neglecting mu probably somewhere, sir, in the equation.
No, 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 mu, no, no, in Navier-Stokes equation, mu is there. But as per the what was the condition, let's say you are going to solve some problem. Uh, I have problem. I have one problem. Let's say your problem is like that. Uh, let's say the not much effect of that, so maybe neglected. It depend on the problem, which type of you are going to solve the problem. But in case of Navier-Stokes equation is always there. I don't know why you are asking where you have seen these things. In the question you have seen, or somewhere where you
No,
have
no,
seen.
here in everywhere it is there. Like even
Oh,
in this.
actually, in this question, what is actually this question you might be seen here. The velocity is. I pen my pen is visible.
Yeah, yeah, visible.
Here you just seen this velocity and this term is zero. So automatically this is zero. You have seen your question is framed like that. Okay, let me discuss. First discuss the question and why you are, I think, talking about this, right? How it eliminated it depend on the question. Question is what is given. Consider a study two-dimensional flow, incompressible velocity field of, that is the whatever, like, and the velocity field is given like that, ax bi and this things, and calculate the pressure as a function of this. The question is talking about you calculate the function, pressure is a function of xy. Let me show first. That is the these things. You calculate this thing, that is your pressure is a function of in x and y. So here what is actually for a given velocity field, we are calculate the pressure field, we are going to calculate these things. The assumption is that the flow is steady and incompressible is given in the question, and the fluid has the constant properties, that is the everywhere mu is and the density is constant. The flow is two dimensional, x and y is there only, and the two dimensional means what, your del w by del z is equal to 0, because there is no velocity in the z direction given in the question, and the gravity does not act either in the x or the y direction, only in the vertical direction is acting on that. So first we check whether the given velocity field satisfy the two dimensional incompressible continuity equation. Yes, if you going to u is what, ax plus b, and v is what, minus ay plus cx. If you will differentiate these things, a here only remaining. If you will differentiate b, what will remaining, only minus a is remaining, so it is 0. So it is follow the continuity equation. Now coming on the next, this is the Navier-Stokes equation is written. Navier-Stokes equation in the that is the next we consider the y component of the Navier-Stokes equation. Let's say the y component is written here. Okay, you know the flow is steady, so 0, and u u was ax plus b, and when you differentiate v, this thing is remaining, just for your, just to see in the general way. And when you calculate these things, and here why it is 0, because of the flow was 2D, and here we going to, this is the w component is not there, and here the gy is we have just assumed above, there is no influence of the gravity in the x and y direction 0. And here your expression lies that like that u is equal to ax plus b and v is equal to minus ay plus cx. If you will differentiate this thing, double differentiate, what first, if you will differentiate first minus a, if you will differentiate double, what will happen? It will be 0. The similar thing will happen with this, so it is 0. And your flow is the 2D, so z component, z differentiation with respect to z also 0. So this your viscosity term is neglected for this question. I think your doubt is clear by this problem. Your uh, Pradeep.
But the whole term is, yeah, whole term is discarded basically because the
Yes,
whole.
because of the problem is given like that, right? But when you will go for solve the problem where it is not 0, if some some
Some piece
expression
of
was, yes,
rotational or irrotational thing is coming, sir, here somewhere. I know. Is it
or
that a rotational or irrotational thing may be coming through? I don't know. Because in case of
rotational component.
we'll get viscosity only in case of rotational flow. Is it not?
Yes,
But
yes, 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 definitely, definitely. If the no, no, actually, your continuity equation, what was above the assumption, your question is framed like that. If your velocity, let's say u was there, ax plus b something ax square was there. So here your double differentiation was not 0. When the double differentiation was not 0, then what will happen? Your viscosity will exist. Here viscosity of the fluid is not going to 0, but the effect of the whatever the other associated term with the viscosity, it is 0. So definitely the whole term will be 0, not viscosity is going to 0 of your fluid flow problem, right?
yeah, yeah,
Yes, so this is the whole concept. And in the last, I will show the some slide. You just take the screenshot of the all student take the screenshot and solve. Try to solve by self. Definitely, you will get some more concept. So now moving on the, yes, the exact solution of the continuity, actually exact solution of the Navier-Stokes equation is very very difficult, and that is the analytical solution. But some simple problem is there. We can solve by the some lots of assumption. So what is the steps? Actually, the steps are there. The first step is this: set up the problem and geometry, that is the sketch are helpful definitely, and identify all the relevant dimensions and parameters. Okay. And step 2 is there: list all the appropriate assumption, what was we have seen in the previous question. That is a very well assumption was written, and the approximation, what you are going to approximate, and the simplifications and the boundary condition, what was the boundary condition. Step 3: simplify the differential equations, what we are done in the previous, what we have done, the just x, that is the flow was 2D, so z component was 0, so this is written here. And equations of motion, continuity and the Navier-Stokes as much as possible. Okay, step 4 is there: integrate the equations and leading to one or more constant of integration. Okay, that is the what was in the previous question was there, that is the C1. So this is the written, and apply the boundary condition to solve the constant of integration. You know, I think from the mathematics, you know, all have the how we can calculate the your constant value, some apply the boundary condition and verify result with your some experimental thing and another thing. So boundary condition, let me explain some boundary condition. No slip boundary condition, you all know this is very very important concept in the boundary condition. In the wall, what was it is written here, in the previous slide I was discussed, when plate is moving and fluid is also moving, if the something is stopped, that is a stationary condition, fluid is also stationary. So here what is actually going to explain in this figure, what this figure is going to explain, this piston is moving, so fluid is moving along the pistons. Your wall is fixed, so along the wall your fluid is fixed. So this is the meaning, there is nothing meaning. When the interface of the boundary condition, at the interface of the boundary condition, uh, your velocity of fluid A and the velocity of fluid B will be equal, and the shear stress also equal. When the, let's say this is also fluid and this is also fluid, but when the interface of the, let's say, the liquid and gas, this is the air and above the air fluid B is air and fluid A is the water. The case of the river flow and open channel flow, you can see, as we have seen the above, what we have seen, the velocity A and velocity B should be equal. So here also written the velocity A and the velocity water and air should be equal, and the shear stress on the A surface and on the B surface should be equal at the interface. Here we are talking about at the interface, not at the top. Here we are talking about at the interface, velocity should be equal. So what is exactly, you know, all the mu of air, that is the dynamic viscosity of air, is very less as compared to mu of water. So it means what, the if the mu is less, you know, all the layer, the upper layer, that is the, let's say the layer is air flow is there, if the viscosity is very less, then it will try to reduce less as compared to the water. If the water layer is there, so the this layer was try to reduce the velocity of this layer, and this is the air, and this layer also try to, but here it is more dominated viscosity, here is the very less, try to reduce the velocity of the upper layer or bottom layer, whatever. So it is the concept is that, and the velocity gradient is and one very important thing is that, if we see in the previous classes, the very less means is that your velocity of water, that viscosity of water is almost equal to the 50 times of the 50 times of the air. So for this condition, if you see this condition, if it is, if you are going to equate these things, tau s of water and tau s of air, if viscosity is 50 times less in case of air, so what is happening, this should be very much, that is the 50 times more as compared to this, that is the your velocity gradient in case of water should be 50 times less as compared to the 50 as compared to the air velocity gradient, because of you are going to equate these things. So it means what, in case of air, very much deformation as compared to this. So the conclusion is that the air, what the water will do, uh, water will try to move the surface, just to air touch with the surface of the water layer, try to move uh, towards the along the flow direction, because of the way, in the case of air, very much deformation as compared to water. Much deformation means uh, by the apply the very less amount of force, uh, it will be deformed, air will be deformed very high, so it will be deformed along with the water. So the conclusion is that, if the condition is like that, here is the water and above the air, what will happen, we generally consider for the mathematical point of view, not exactly. The CRA stress on the surface, on the top surface, is almost zero in case of interface, and the the pressure is related with the velocity, so the pressure of liquid is equal to the pressure of gas. So this is the concept of the boundary condition at the interface. When the two fluid, that is two liquid, is acting, then your shear stress definitely will be the equal to the upper layer or bottom. But when the air and the liquid will act, the shear is, there is no concept of the, we are neglecting, there is no harm for neglecting the shear stress from the top. So this is the whole concept was the boundary condition, and some example I have. So if you want screenshot, you can take the screenshot of the exact solution of the Navier-Stokes equation. I think you got understand about the boundary conditions. So please, if you want, you can take the screenshot of the questions. I have one, two questions. It is done. This slide, the question of this.
Yes, yes.
Yes, you can take
Yes,
the,
sir.
yes, the stepwise. Actually, what I was discussed, the 7 or 8 steps or 6 step. The stepwise given. You, when you read this question, you definitely get the your concept. You will definitely get. You take the screenshot of this also. Now this is also the similar. The same question is going. The step 4 and 5 is there, and step, and how velocity is varying the linearly. Here it is, if you solve this question you will see. And one, where is the application of these things, I have also slide where we are going this. We have whatever I think the question was about the, this example where we are going to apply this 9.15 example. The application, the step 6 is there for verifying the result, how we will
So
verify.
code flow means viscous flow.
Yes.
Is the code flow means viscous flow?
Yes,
Uh,
viscosity is there in the, yes. Oh, now here is the application things. Here is written very well. You may be the questioning the useful of the final result of the example, above example. After all, you know the application of this is what? This is the viscometer. We are calculating the viscosity using this. So this formula is very, very important. You must have to remember these things. So we are going to utilize these things in the calculating the viscosity of any fluid. You can take a screenshot if you want. And another question is there. In the previous question, the pressure gradient was not there, but the similar question is there. Only the pressure gradient applied on the at actually at the inlet point. So how will different? How will result will the different from previous solution to the this solution? Only the, in the previous the pressure gradient was zero, but here is the pressure gradient is there. So you take the screenshot of also. That is step 1, 2, 3 is there. Step 4 and 5. And if you see the difference, you definitely will see. The difference is that this thing is extra. Only velocity was in the previous case uv by h, but here is the extra thing is there. Step 6 is there for the validation. So this is the whole, you take the discussion thing also. So this is the whole concept of your Navier-Stokes and all. And the Francis, your doubt was also clear today. If any student having the more doubt, you mail me. I will try. I will try to give my best 100% to all of you. Okay, bye bye. We'll meet again on the next Monday. Francis, if you want to tell something.
There was a question, the first question that I sent about that velocity and pressure lines to keep it in order. How to keep
Okay, okay, okay. Okay, oh, friction term. Okay, okay. No, no, no. Actually, what was written? Actually, generally, we write the. Oh, these things I forgot putting in the slide, but no problem. I will explain. I am.
so actually, is that question correct? Is there any problem with the question?
No, no. Actually, what was explaining question? You know the about the. Let me explain verbally. Actually, you know the losses is there in the pipe due to the friction thing.
Yes, sir.
Yes, so that is why the friction head was there. Friction head means is not friction head means is there, maybe it's a negative head, that is your head will be going to reduce due to the friction. This was written. I think order is there, that's why order is written, because of the generally if you going to represent some, then first you represent the datum, then after your static, then after your velocity head, then after you just represent the this much is reducing from due to the your friction head. So I think question is like that. If I think I didn't get the order thing, why he was asked the question was asking the order how we can. I think it is just as per the representation point of view, how we can represent these things. So I think your friction part is friction head was indicating the friction loss in the pipe.
Okay, sir.
Yes. Okay, we'll meet again in the next class on the Monday. I think we have the 2 weeks, 11 and 12, and after 2 weeks we have one summary class. What was your doubt? You just mail me, and we'll try to. I will try to solve within. Maybe I summary class was only the 1 hour, maybe the 2 hour also, no problem. So we'll talk more in the summary class about your the whole problem from beginning to 12 weeks. We'll meet again in the next week with week 11. That is the boundary layer concepts. Okay, bye bye.
Thank you, sir.
Thank you, sir.
Thank
Okay,
you, sir.
Thank
okay.
you.
Welcome, welcome.